So, welcome to this class on hardware security. So, today we shall be continuing with our discussions on elliptic curve crypto systems and their implementations. So, we were discussing in the last class about the Montgomery's technique of scalar multiplication. In particularly, today we will be discussing about how to perform a fast scalar multiplication with only one coordinate system, that is only x coordinates. So, we basically do not need the y coordinates, and that is a very efficient way of doing this operation. We shall be talking about projective transformations to reduce the inversions, which are very costly in terms of computations. We shall be looking into another alternative technique which is also adopted by some designers, which is called as the mixed coordinate systems, where one coordinate is kept in projective coordinates, whereas the other one is kept in affine coordinates. And then finally, we shall be trying to talk about parallelization techniques. So, let us see what we can cover. So basically, like we were discussing about this form of the curve, which is defined over characteristic two fields, where x and y are elements of GF2 power of m cross GF2 power of m. And we basically stopped in the last class about by noting that the x coordinate of the doubling operation, that is when you are doubling p and p, that is you are computing 2p, then the x coordinate of 2p depends only upon the x coordinates actually of p. So, it does not depend upon the y coordinates of p. So, therefore, that is an important observation, and we also discussed about that that we can potentially write or perform the computation in a manner, so that we can only do we can also do the addition in a similar way with only the x coordinates. So, that essentially is the basic crux of Montgomery's method, and let me introduce that. So, in Montgomery's technique, the objective is still to compute the scalar multiplication. So, you have got a scalar k and you would like to calculate k into p. So, k is your scalar, which is say like the binary expansion of that is denoted by this kl minus 1 to k 0, okay, and I want to calculate k into p. So, the technique is that we introduce two registers p1 and p2 such that p1 is p and p2 is 2p. Okay. So, the idea is that p2 minus p1, if I calculate, right, p2 minus p1, therefore, that is 2p minus p. So, that is p. Okay. So, what we try to do is we try to do this computation in this ladder in a manner such that 2p like p2 minus p1 is always equal to p. So, that remains an invariant in this computation. Okay. So, if you see like how you can do that is as follows, very simple. I want to compute from, again like assume that L minus 1 is 1. So, this is again from the MSB we are computing. So, if I compute from the MSB, I am assuming L minus 1 or KL minus 1 to be 1. So, let me try to start processing from KL minus 2. So, therefore, write the KI over which I am basically processing at a current iteration. So, like the iteration will vary from L minus 2 down to 0. So, at some ith stage, if the KI bit is 1, then I do an addition in the register P1 and I do a doubling in the register P2. Okay. Alternatively, if the bit is 0, then I do an addition in P2 and I do a doubling in P1. Okay. So, if you do that, then the first thing which you observe is that P2 minus P1 remains an invariant, okay, because you see P2 minus P1 is always equal to 2P2 minus P1 minus P2, and therefore, it does not change. Okay. Likewise, if you calculate if it enters this part of the loop, then P2 minus P1 is still equal to P2 plus P1 minus 2p1, which is again equal to p2 minus p1. So, it still does not change. Okay. So, therefore, the idea is that in both these computations p2 minus p1 remains an invariant, and since I initialize p2 minus p1 to p, it remains p throughout this computation. Okay. At every stage of the iteration, p2 minus p1 is the base point p. Okay. So, therefore, right, what is the advantage of this? So, if I want to really understand that, then we have to go across like some results that we will develop one after the other and try to see how we can do this computation. Okay. The first thing is, let us see the correctness before I go into that and get into the implementation aspects. So, suppose I want to calculate 7p, again taking the same example as we were talking in the last class. So, therefore, I have got 1 1 1 as my binary expansion of 7. So, I initialize P2 to 2p and P1 to p, okay, and therefore, right, if the bit is 1, I do an addition in P1. So, basically I add p with 2p and I get 3p, okay, and in P2 I do a doubling. So, P2 becomes 4p. Okay. Likewise, when the bit is 1, again I mean in next iteration as well, I add I add 3p with 4p, so I get 7p, and I double 4p, so I get 8p. So you can see that I still get 7p, which is my objective. If the expansion was for 6, okay, so this will be 6. Okay, so if it was 6, then I have 1 1 0. So again I initialize p and 2p for p1 and p2 respectively, and since this bit is 1, I essentially do an I do an addition. So I do an addition in p1, that is p plus 2p is 3p. I do a doubling, which is 4p, but since this bit is 0 now, I will do an addition in p2. Okay. So therefore I add 3p with 4p, I get 7p, but I double essentially p1. So if I double p1, then from 3p I get 6p, and note that p1 is the value, or the final result is stored in p1. So it correctly computes 6p. Okay. So you can also prove this in a very generic manner about the correctness, but intuitively we understand that this algorithm works quite okay. But then what is the advantage when you are doing the computation in this manner? So the idea is that this was essentially one of the first results which actually tells you how to do elliptic curve scalar multiplication without storing any result. Okay. Previously, like when you wanted to compute say 7p, often one technique was that you store powers of 2, okay, as scalars. So for example, I store 2p, 4p, okay, 8p and so on, and then when I am doing a computation, I runtime combine these results and I get or return the result. Okay. But in this case, I can do it very efficiently just by computations without any explicit storage, and most importantly, I operate in the Montgomery ladder in only one coordinate, not in two coordinates. Okay. So the first result that is of significance here is this, that is, if p1 is x1 comma y1 and p2 is x2 comma y2, then the next coordinate of p1 plus p2 is x3, and it can be computed by this equation. Okay. So this essentially we can work out this result. So this result essentially will derive, or we will essentially derive from from this equation, that means from this addition equation. Okay, and of course with some more simplifications. So let us try to do this computation. So basically, like what we essentially can do here is we can start. Okay, so let us take for example the points x1 comma y1, say x1 comma y1 and x2 comma y2 as the 2 points. Okay, so I want to add them. So therefore, right, by using the equation that we had, essentially we have got x3 equal to y1 plus y2 divided by x1 plus x2 whole square. Okay, I am just rewriting the equation that we had, y1 plus y2 divided by x1 plus x2 plus x1 plus x2 plus a. Okay, right. So now if I simplify this, then in the denominator I have got x1 plus x2 whole square, and in the numerator, since its characteristic 2, right, all these elements x1, y1, x2, y2 are characteristic gf2 power of m elements. So therefore I will have y1 square plus y2 square, okay, plus this x1 plus x2 into y1 plus y2. So therefore I can write x1 y1 plus x1 y2 plus x2 y1 plus x2 y2, okay, plus some more terms, that is, if I simplify this, this would be something like x1 cube plus x1 squared x2 plus a x1 squared plus x2 square x1 plus x2 cube plus x2 square a. Okay. So this is my result of the computation. Okay. So maybe you can verify this. So note the fact that p1 comma that is x1 comma y1 and x2 comma y2 are points on the curve. Okay. So since they are point on the curve, therefore I can write that y1 square plus x1 y1 plus x1 cube plus ax1 square plus b is equal to 0, and likewise and
y2 square plus x2 y2 plus x2 cube plus ax2 square plus b is equal to 0. Okay. So, therefore, what we have, if I write here, right, and arrange the terms, then and keep the denominator as x1 plus x2 whole square. Okay. In the numerator, we will have x1 y2. So, basically keeping these terms x1 y2 plus x2 y1 plus x2 y1, and the remaining two parts are nothing but these things like y1 square plus x1 y1 plus x1 cube plus ax1 square plus b, okay, plus y2 square plus x2 y2 plus x2 cube plus ax2 square plus b plus x1 square x2 plus x2 square x1. Okay. So, you can note that I have just added a b here, and I have also kind of adjusted the b here. So, because they are characteristic too, so we can do that, and this essentially and this part essentially are both 0. Okay. So, therefore, right, finally, I have got this result where I can write the numerator. So, the denominator is x1 plus x2 whole square, but in the numerator I have got x1 y2 plus x2 y1 plus x1 square x2 plus x2 square x1. Okay. So, this is essentially nothing but the addition operation, and essentially that is the like the result that we have here, and that essentially is very much this equation. Okay. So, now once we have this equation, we can actually go to the next result, which essentially tells you that now with x, remember that x comma y is suppose the point for p, okay, I mean the x is the point p, then you can actually like the doubling x3, okay, you can also write the addition x3 only in terms of x1, x2 and x. Okay. So, you now note that x is predetermined, is already known, and therefore, the entire computation is devoid of any y coordinates. Okay. So, this result is also can also be derived quite easily, and essentially we can we can see this derivation also we can also do this derivation in a similar fashion. Okay. So, let us try to do this derivation. So, to start with, I essentially note that the point P is nothing but P2 minus P1. Okay. So, this point P is P2 minus P1, which means that x comma y is nothing but x2 comma y2, okay, plus minus P1. Okay. So, what is minus P1? So, remember that we derive this. So, if x1 y1 is P1, then minus of P1 is nothing but x1 comma x1 plus y1. Okay. That, so, if this is P1, this is your minus P1. Okay. So, therefore, there is nothing but addition with x1 comma x1 plus y1. Okay. So, therefore, now if I apply the previous result that we derived, then I can write x as the denominator is x1 plus x2 whole square, but the numerator, right, is x1 y2 plus x2 into x1 plus y1 plus x1 x2 square plus x1 square x2. Okay. And also note that, and we already know that P3 is the result of adding P1 and P2. Okay. That is what I am trying to derive. So, therefore, right, trivially I can write that x3 is equal to x1, I mean again I can write the similar stuff for x3, and I can write this as x1 y2 plus x2 y1 plus x1 square x2 plus x1 x2 square. Okay. So, that means that if I add up these two parts, or if I add up x with x3, then you note that all the terms gets cancelled out except x1 x2 divided by x1 plus x2 whole square. Okay. So, therefore, I can write x3 as nothing but x plus x1 x2 divided by x1 plus x2 whole square. So, here I mean you see that I need to do an inversion operation, that is I need to calculate 1 by x1 plus x2, but then I need to multiply with x2 and with x1. So, I need to do two multiplications. Okay. So, one way of kind of optimizing it further would be to write this as x plus x1 by x1 plus x2 plus x1 divided by x1 plus x2 whole square. Okay. You see that if you do that, then you are doing one inversion and one multiplication with x1. Okay. But essentially it is the same computation that you are doing. Okay. So, therefore, this is the final form that we will take, and you see again that we have completely eliminated the y coordinate and essentially are operating only on the x coordinates. Okay. So, with this I mean we can now get back to the slide and we can see that essentially that is pretty much the equation which is written over here, x plus x1 by x1 plus x2 whole square plus x1 by x1 plus x2. Okay. So, likewise you can actually so but you see that finally when you are doing the computation, you essentially have to come and finally return the output point, that is x3 comma y3. So, you need to still compute y3. Okay. And so, therefore, at the end of the computation you have to essentially somehow have that information of y. Okay. And using this result 3 we can do that. So, the result 3 says that if p is equal to x comma y and p1 is x1 comma y1 and p2 is equal to x2 comma y2 with the elliptic points, okay, assume that p2 minus p1 is equal to p, okay, and x is not 0, okay, then the y coordinate of p1 can be expressed in terms of p and the x coordinates of p1 and p2 as follows. Okay. So, you see again using the result I have obtained. So, remember that p1 is my final result, right, in the Montgomery ladder p1 is the final result. So, therefore, the x1 of p1 is my important x1, okay, is the important information. What I am showing in the result is that from x1 and from the other information like x2 for example, you can actually pretty much compute y1. You can compute y1, and once you have x1 and y1, you have the coordinate, you have the result basically. Okay. So, I am not going into the derivation, okay, of this result, and I leave it to as an exercise to verify that this is correct. Okay. So, now if I put all these things together, okay, so what you see here is that I have pretty much all the pieces now to compute the scalar multiplication algorithm in the affine coordinate system. So, therefore, this is my scalar, and now what I am basically doing is I am doing this computation only using x coordinates. Okay. So, I basically initialize x1 to, remember, only x1 was supposed to initialize to p, okay, and that is equal to x, and x2 was supposed to initialize to 2p, okay, and this is the x coordinate of 2p. So, therefore, I have got x square plus b by x square to initialize x2. Okay. So, now from L minus 2 to 0, what are the steps that I have to do? Remember that if the key bit is 1, then I do an addition in p1, okay, and I do a doubling in p2. So, that you can easily understand by this, that is I do a computation like t equal to x1 by x1 plus x2, okay, and that is an intermediate computation that I do, store it in a temporary variable t, and then I compute x1 which is nothing but the x coordinate of p1 plus p2, okay, and therefore, I get x1 plus t squared plus t as my resultant x coordinate. Okay. x2 stores a doubling, right. So, therefore, it stores a doubling of p2. So, therefore, I can compute x2 square plus b by x2 square. Okay. Likewise, if the key bit is 0, then I just do the opposite. I do a doubling in x1. So, therefore, I get x1 equal to x1 square plus b by x1 square, and in x2 I calculate x plus t squared plus t. Okay. So, note that once you have done this computation, finally you get the result which is x1, but somehow I need to calculate y1. Okay. And for this as I apply result 3. So, what I do is I calculate say x1 plus x, I calculate x2 plus x, and I denote that as r1 and r2, and then I apply result 3 to get the corresponding y coordinate, and then I return x1 comma y1 as my resultant output. So, note that in this computation or in this loop, right, I have been operating only on x coordinates. There are no y coordinates
So basically you kind of like save lot of computations, also save lot of resources potentially if you're thinking of a hardware design. Okay. So let us calculate the cost. Of course, you can calculate the number of inversions, multiplications, additions and squarings which are required. Most importantly, let us see about the number of inversions, because inversions, as we have seen, are pretty complex in composite fields. I mean in Galois fields. Okay. So therefore, right here, when you see when you are computing the number of inversion, you see that there is one inversion which is required at the beginning when you are doing an initialization. So that is one extra inversion which you have to do. Inside the loop also you are doing two inversions. You are always doing this inversion, and you are either doing this or you are either doing this. Okay. So therefore, there are two inversions in the loop, and there are L minus 2 iterations in the loop. So therefore, the number of inversions can compute to 2 into L minus 2 plus 1. Okay. Likewise, you have got multiplications, additions and squarings. You can essentially verify that these results are indeed correct. Okay. And essentially what you would of course want is to reduce the number of computations, but in a plain vanilla format, this is the number of computations which you have to do. Okay. So now there is what the designers wanted to do is they wanted to reduce the number of costly inversions, because inversions are pretty complex, and typically as a thumb rule, right, you will see that one inversion is equivalent to roughly 7 or at least more than 5 multiplications. Okay. So therefore, right, what we would like to do is we develop techniques so that we can optimize these computations. So one of the techniques which is very powerful in this context is what is called as to go for a 3 coordinate system. So in affine coordinates, what we are till now working on, we have got 2 coordinates, x and y. In projective coordinates, as it is called, we have got 3 coordinate system. So we got x, y and z. Okay. So therefore, right, what we say is that if you are given an like 2 triples like x1, y1, z1 and x2, y2, z2, then they are said to be equivalent if there exists a non-zero element lambda which also belongs to the finite field, such that x1, y1, z1 is nothing but lambda x2, lambda y2, lambda z2. Okay. So the equivalence class is often defined only by ratios like x is to y is to z. Okay. So therefore, right, let us see about how we can apply this technique to reduce the number of computations. Okay. The basic idea is that you have got a 2-dimensional projective space and over K, and it is given by the equivalence class of triples x, y, z with x, y, z in K and at least one of x, y, z which is non-zero. Okay. Then and this is the like definition that 2 triples are essentially equivalent. So this is how you relate to such points. Okay. So now, how do you apply them? So that is most important. So therefore, right, what we do is typically we basically take the affine coordinates like x, y, okay, and transform that into a projective domain, in the projective domain. So what I do is that I basically like write as x by z the x coordinate and the y coordinate as y by z. This is there are many projective coordinate systems. This is one such projective coordinate. Okay, where I write say. I basically try to do is that if the z is not equal to 0, then I say this ratio x is to y is to z is nothing but x by z is to y by z is to 1. Okay. If z is equal to 0, right, then that essentially defines the point at infinity. So if you ever get z equal to 0 when you are doing your projective coordinates, then that means you have computed the point at infinity. Okay. So therefore, right, let us try to see how we can do this computation. So of course, like we have to see the advantages, and only if it is advantageous, because there will be some like increase in computations also when you are converting from the affine coordinates to projective coordinates. What you have to see is that the increase or the cost that you are paying, whether it is giving you benefits. Okay. So the whole idea, right, whether you should go into projective coordinates will define upon your m is to I ratio. That means the cost of the multiplier compared with your inversion circuit. Okay. So let us see how we can reduce the number of inversions, okay, in a more take a more concrete case. So and I hope that this will become more clear. Okay. So in affine coordinates, inverses are very expensive. For n greater than or equal to 128, each inversion requires around 7 multipliers in hardware designs. Okay. So one such one popular projective coordinate system is what is called as the LD coordinate system or Lopez-Dehab projective coordinates. So what is done in these coordinate systems is that if I have got a projective coordinate like x, y and z, okay, and z is not equal to 0, which means this is a finite point. If z equal to 0, then it is a point at infinity. Then this maps to x by z and y by z square. Okay. So the motivation of this is so now what I can do is that this is my relationship, that if I have got a projective coordinate x, y, comma, z, and I want to transform it into the affine coordinates, then I just calculate x by z and y by z square. The idea is that the motivation, as I am saying, is to replace inversions by multiplication operations, okay, and then perform one inversion at the end. So that means the entire operation will be only doing on multiplications and additions, but no inversions. But finally there will be one inversion which is required to bring the result back from the projective coordinates to the affine coordinate systems. Okay. So let us relook at the equations, okay, to understand this. For example, this was my equation which we essentially derived for doing the doubling in the projective coordinates. Okay. So if you remember so let us take an easy example when we are considering the doubling, for example, okay, and the similar thing can be done for addition as well, okay, which I leave probably to as an exercise. Okay. So let us see this equation, x3 equal to x1 square plus b by x1 square. You can easily see that if I want to do this computation, I need to do one inversion operation, okay, because I have to do 1 by x1, I have to calculate this 1 by x1. So now let us see how we can transform this into the projective coordinate system. Okay. So the idea is that what we do is we have to do this computation. So the computation that is required to be performed is x1 square plus b by x1 square. Okay. So now my projective my computation, right, as I said, using the Lopez-de-Haab, right, is x by z, y by z square. This is my like if I have got a point, say x, y, z, then and if I want to write that in the affine coordinates, then my representation is x by z and y by z square. So therefore, right, if I just take this and I plug it into this equation, then what do I have? I have got x by z whole square. So I am just writing from this x by z whole square, okay, plus b divided by x by z whole square, right. So that implies that this is nothing but z square x square in the denominator, and the numerator is nothing but x to the power of 4, okay, plus b z to the power of 4, right. So this is your corresponding result in the in the affine coordinates. So therefore, right, what we will do here is we will actually calculate. So now imagine that the computation is done in the projective domain. Okay. So in the projective domain, you are basically, so if you compare it with the affine domain, what you are doing is in the affine domain you have got x1 comma y1. So actually you have got x1 in this case, which is required. You are basically calculating x3 from there, right. This is in the affine domain. But in the projective domain, now you have got x1 comma y1 comma z1. From there you are calculating x3 and z3. Actually, like as I said, that we don't need y1 because of the advantage of the Montgomery ladder. We are basically operating on x1 z1 and calculating x3 and z3. Okay. So therefore now if you compare this, consider this as your x3. So then that implies, because of the like if you see the Lopez-de-Haab representation, then this stands for x3 and this stands, or the denominator stands for z3. So that means now I can process the numerator and the denominator separately. Okay. So this is essentially nothing but my x3 equation and this is my z3 equation. Okay. So likewise, right, even if you see the addition operation, when you are doing addition, you also see that you can process the x3 and the z3 separately. Okay. So there are no inversions which are required. So of course you can, if you compare, you see that there are 0 inverses which are required. Okay. So if you see that this is your cost for doing the doubling and the addition in the normal affine coordinates, in the projective coordinates you see that there is an increase in the number of multiplications. For example, you are going from 1 to 4, okay, but what you are saving is this costly inverse. Okay. So therefore the advantage of going from affine to projective coordinates will only come if your inverse circuit is complex. Okay. So therefore for smaller fields this may not be so advantageous, but for normal fields or the fields of usual dimensions in elliptic curves which are pretty large or reasonably large, you will find that this should be advantageous technique. Okay. So, therefore, right, what we will see in our future discussions is that whenever we are trying to do an hardware or develop an hardware design, usually we use the projective coordinate system, because we want to reduce the number of inversions. So, finally, right, I mean, when you get the result, so now you can essentially do the Montgomery ladder entirely in the projective coordinates. So, essentially I have done exactly nothing, but I just written x1 equal to x. So, you see I am just processing only on x and z's, because I do not need the y coordinates. Again, it is just we have written the x2 to store the doubling operation, and that is exactly the equation that we derived in the last slide. And then in the iteration or in the loop, we basically do an addition in x1 y1 x2 z2 and do the doubling. So, these are all projective coordinate additions and doublings, and likewise you are doing addition and doubling in x2 z2 and x1 z1, or doubling only in x1 z1 if the key bit is 0. Okay. So, finally, right, when you get the result, you have got x1 y2 and x2 y2, but you need to again bring back that to the affine coordinate system. Okay. And there you essentially have to do one more inversion. Okay. Because here you see that I essentially need to bring the result back to the from the projective coordinate system to the affine coordinate system. So, I need to do this x1 by z1, and that is easy to do, but in the y3 I have to do few more computations. Okay. So, the y3 is again a manipulation that you have to do depending upon the equation that I showed to you in result 3, which essentially will bring you back the result. Okay. And finally, right, you will see that this entire operation will require 10 multiplications and 1 inversion. Okay. So now I basically leave it to as an exercise to think that why you need 1 inverse. Okay. Because you see that it looks like you have to do a 1 by z1 here and a different inversion here. Okay. So, I just leave it to you as an exercise to think about how or why you basically need 1 inversion to do this operation. Okay. So, therefore, right, let us try to finally make a comparison of the affine coordinates with the projective coordinates, just to see the benefits. Okay. So, you see that in the affine coordinates, these are the rough nomenclature of the, as I said, that you have to do 2 into 2 log k. To log k is typically denoting the dimension of the bits. Okay. So, we derived that it was 2 into k minus 2 plus 1, or 2 into l minus 2 plus 1. Okay. And that is basically written here as 2 log k plus 1, kind of denoting the number of inversions which you have to do. Interestingly, in the projective coordinates, you have to do only 1 inversion. Okay. And that is the benefit. But at least you can also understand that there is a cost. The cost is in terms of multiplications. The multiplications has increased. So therefore, right, the question is that whether the final decision whether you will go into the projective coordinates will depend upon your I is to m ratio, that is the inversion is to the multiplication ratio. Typically, right, if it is more than 5, like if it is around 7, then we go into the projective coordinate systems. Okay. So finally, there is there is a technique also which is called as the mixed coordinate systems. In mixed coordinate systems, what you do is you basically keep one point in the affine coordinates, whereas the other point is so suppose you have got 2 points, p1 which is x1 by z1, y1 by z1 squared, and p2 is x2 by z2 and y2 by z2 squared, be 2 points on the curve. Okay. If z1 is 1, if z1 is 1 implies that this point is an affine coordinate point. So, if p1 is affine and p2 is projective, then also you can calculate p1 plus p2. Okay. And here are some equations to do that, and I am not getting into the derivation of these equations, but what I would like to mention here is that there are some papers or some results which shows that the number of multiplications are further reduced. Okay. Most importantly, squaring is increased a bit, but they are cheap in gf to the power of n, as we have seen. So roughly the results show that if a is not equal to 0, then there is an improvement of 10%, and if a is equal to 0, then there is an improvement of 12%. Okay. So therefore, it makes also sense to keep one point in affine coordinate and the other point in projective coordinates, and to do the computations. Okay. So let me stop here, and we shall continue with some more discussions about how we can parallelize it and eventually go into the hardware design of elliptic curves in the next class. So thank you for your attention.